Okay, first problem we are doing, given as power rpm d naught given as 1.5 di. This is the outer diameter and inner diameter given in the question. Material is woven asbestos with steel. Yield stress of the material is given, factor of safety is given, and the condition is uniform wear. Step 1, we have just identified the equation of power, very general equation. So from this we'll get the torque. It's direct substitution. Right. So what is the torque? 230 into 60,000 over 2 into 5 into 1,200. Okay, so this value getting as 238.73 238.73, and this value here will be in this is in Newton and meters. So this will be in Newton meters. So we need to convert this to mm. So let's put the same thing. We'll put it in mm. So this will be nothing but into then raised to 3 and in mm. Now this is in Newton mm. Right. So this is the value of torque. So let's put it all in mm. And permissible shear stress 50% of 324 divided by 2.5 is giving us 64.8 Newton per mm square. So this here. Okay. So right. So we have both values. We can substitute directly here. Let's copy this. So torque already found. This is the value of the torque. Put a multiplier here into pi into permissible shear stress is this value here. Use this. Right. So find out the shaft diameter using this equation. We'll proceed to step 3. Okay. So step 3 is mean diameter of friction line. Step 3 will say mean dia of friction lining. Mean dia of friction lining given under uniform wear. Okay, the condition is given in the question. There is uniform wear. Okay, don't use the uniform pressure one. So we need to omit this and use only this equation. So DMW meaning diameter of mean diameter considering uniform wear. That's meaning. Let's say DMW. So this will put it on a subscript. The DMW equals on a fraction is D naught plus di over this average. So we'll put on a subscript. Okay, so this equal to, I think in the data is given d naught in terms of di. That is 1.5 di. So therefore, we can substitute one in terms of the other. And do we know the mean diameter? No, I guess. Don't know the mean diameter yet. So we can substitute one in terms of the other, and we can know what happens. So this here is 1.5 times di as given in data. So that means this is fraction of 2.5 times di over 2, which means this is 1.25 times di. So we'll keep this as it is. Okay, that means dmw. This is the mean diameter, is nothing but 1.25 times the interior diameter, inner diameter. Okay, so that's it for step 3. Let's move on. So step 4 is the axial force needed to engage the clutch. So let's just say step 4, axial force needed to engage the clutch. Just say that and go back here again. For uniform pressure in uniform wear, you have two different equations. Let's since it's given as uniform wear, we'll use this equation, which is given in equation 13.9d. This is Mahadevan data handbook, which I have uploaded already in edit. Only download that and use it. This is 13.9d FAW. Let's say FAW is axial force, which is required considering wear condition. This is half pi P max. Let's say 1 over 2 half. Then you have pi. You have P max. So let's use a small p here because it's the pressure. Don't confuse it with power. Okay. This P max is maximum pressure here. P max di into this is d naught, do. This is do, outer dia to inner dia. So this is given in equation. What is that? 13.90. I think even this one is in the previous one also. I'll write up 13.9. This is equation 13.9. The data handbook already posted on Edit. You can download it and keep it somewhere safe. Right? So we need to get here P max to find the axial force. We also don't know the interior and the outer diameter. So what we'll do, we'll do everything and find in terms of pi. So but first we need to find P max here. So what is P max? So P max, I've told you in the steps, is the maximum allowable pressure in the friction lining, referring from table 13.4. In table 13.4, P max is here, right? So P max you'll get from here, depending on what is the material. What are the materials which are there together? So we have woven asbestos or steel. We have two values for the same thing here, and these are distinguished by, I think, some amount of coefficient of friction, either wet or dry friction. Okay, so here it is not given whether it is wet or dry, so that information is not given. So what we'll assume the first one. So if it is wet, now we need to assume this line here. Okay, and if it is dry, I think we need to assume this line here, because it's blank here. Some kind of balance we need to do. So this, let's assume this value, woven asbestos coupled with steel, and let's take this as the coefficient of friction as a dry. Okay, let's take mu value between 0.3 to 0.6. That's an average of that. Let's say let's take off Pmax first. So Pmax will be in between 0.34 to 0.69. This is 0.34 to 0.69. The units are meganewton per meter square, which is again Newton per mm square. So we can use that Newton per mm square itself. Okay, so we'll take an average of this. Say 0.34 plus 0.69 over 2. We got 0.515 Newton per mm square. That is the maximum pressure. Yeah, I think that's it we can do. One more thing we can take mu, the coefficient of friction considering the dry condition. So between 0.3 and 0.6. So this we'll write off from table 13.4. Again, the value of mu is 0.3 to 0.6. So this I think averages around 0.45. We'll keep it like that. And this is from table 13.4. So both values P and mu. Let's keep it. Maybe we'll find you some other time. If it is given, is not given wet or dry. So that's why I've taken assumed dry and taken this. If it's wet, you need to assume this and take these parameters respectively, right? Right. So next, we need to solve this, right? So let's simplify this further. Use this equation here, and now we know P max into 0.515 into di, and d naught also will write in terms of 1.5 times di, right? 1.5 times di, right? So simplify this. See what you get. FAW equals in something in terms of di, I guess. So 0.5 into 0.515 into 5 into, there's minus here, not plus. Okay. So this again will amount to 0.5. I get that piece into 0.5. So I'm getting 0. No, not here. FAW will be 0.40405 times di squared. Okay, because you already have one di here, that is internal diameter. There's one more here which will amount to a square. So we can't do anything else. So let's keep it like this for now. Okay, next step. Say step 5. Step 5 is power transmission capacity. The last step before we combine the procedures and find the dimensions. So MT mu is mu. We will use mu here. So you see this n dash here. So n dash is the number of plates, pairs of friction surfaces, this kind of stuff. So you're considering uniform wear, torque transmission capacity. Let me put this. This is torque transmission capacity. Torque transmission capacity given by MT is directly given the equation in the data handbook. So MT equals this value, half mu n dash F AW DMW. So let's say half, then you have pi, then you have n dash, then you have F AW is the where, then you have DMW, that is the mean diameter. Mean diameter considering the wear condition. So this is given equation. Equation 13.9. I think you'll find everything in one single page. Only 2 pages you need to keep for this class. Right. So we know mu is this value here, 0.45, just an average of that. You can choose any value in between, not mandatory that you take an average only. Then n dash. N dash is the friction surfaces, pairs of friction surfaces. So you have only one pair, one friction lining with that steel. So n dash in 1. The FAW we've already condensed it to this much. Right? This is FAW, and DMW I think we have found out in the yeah, here. DMW is the mean diameter of the friction lining. So we have everything. We can just directly substitute here. So our transmission capacity is mu, that is 0.45 times n dash is 1 times this FAW value this into this 1.25 di. Right. So let me simplify this further. So MT here will be, let's simplify this. So 0.5 into 0.45 into 0.405 into 1.25. So this is coming around 0.114. Then you have d square, di square, and into again another di. You'll have a cubic value. Right. We're almost at the final stage. The next stage for design, we need design, right? For design, MT, suppose close in brackets, MT and capacity. This is what we have just found out in step 5. This should be greater than or equal to. We have a symbol like this here. It should be greater than or equal to transmitted. So to be transmitted. So this is a condition for design. So whatever this capacity is there, it should be greater than or equal to the transmitted one. So this should be greater than or equal to transmitted. We'll get it from step 1. That is this value here. Okay, so from this we will get what is the internal diameter. In turn, we will get the external diameter E naught, which is 1.5 times di. Right. Again, from this we will get the mean diameter. This dmw. dmw is 1.25 times di, and also diameter of shaft. Okay, so all these dimensions are required to be find the final result. So internal diameter, anybody? Let's find out. I'll go for this. This was required to be found still. Diameter of shaft, that is 16 times 238.73 E3 over 5 times 64.8. So square root of this answer is 136. It's a cube root. Sorry, small mistake here. This is a cube root. How do I input cube here? Is there any option to input cube? Okay, so there is no option here for inputting the cube root. It is actually a cube root. You make a small change here. I'll just put here. Put. Okay, I forgot to put here. So there's a 3 here. You make a small change. There is a cube root here. There is a cube root of this value. So that means here also it is a 3. Therefore, let's say, okay, so cube root of this you get around 26.57 mm, and we'll approximate this. We'll approximate this to 27 mm. So we got D. This is the diameter of shaft. Diameter of shaft is this much. Anybody got DI? Internal diameter is 238.73 E3 over 1.114 and cube root of that. So that value comes around 127.94 mm. we can approximate that to for a value of 128 mm. If that is 128, which means 128 times 1.5 is 192 mm. Then mean diameter 128 times 1.25 mm will be 160 mm. Right. These are all the key dimensions which are required to be found. As you can see, a little bit very simple than compared to gas. Very few equations to substitute, and this is pretty straightforward. This is step by step. You can just solve this. Right. So, any doubts you have, just post in the chat.